Hello and welcome back to our lecture series. Emeka Udenze is speaking once again. Today we'll be looking at the second part of the review topics for this second part of the GOB lecture. So we'll look at the review of critical topics 2. We started with the first part, and this second part we're going to be covering a few other ground. Now, but before we do that, I have a beautiful quote for you. It says, "Shoot for the moon, even if you miss, you will land among the stars." This quote was from Les Brown. It's just for a food for thought. Now, what are the things I'm going to be covering in this lecture? They include the following. Number one, we'll look at what I call the line angle structures, which is another way. In the last lecture, I taught you about condensed versus expanded structural formula. The expanded structural formula, you can say expanded or extended. Now, but we're going to bring in another way of writing these structural formulas in a short form, which we call the line angle or skeletal structure. So that's what we're going to bring in. Then we once again revise the VSEPR model, which is the valence shell electron pair repulsion model. Now, usually what we do there is that we look at how to add lone pairs, bond angles, and then formal charges. And then we now look at the polarity of molecules, which is going to be playing an important role in this class, particularly when we study organic compounds. We study their nomenclature, their physical properties, and their chemistry, and their chemical properties. Now, that physical property is usually what we look at is what? The color, their polarity, which has to do with how much they react, how much they dissolve in water or not. And that will affect their boiling and melting point. So that's what we're going to, and finally, we'll look at the definition of oxidation and reduction in terms of oxygen and hydrogen. Let's take it off from there without wasting time. Let's start with the line angle stroke skeletal structure. Line angle and skeletal structure simply means a way of representing structural formulas of organic compound using lines. Usually we use lines. I like using my red to do this. We use lines to represent the bond. We use lines to represent the bond. That's what we do. Now, each line, of course, anytime you draw a line, there are two ends, right? Each vertex, listen now, if I draw a line starts with a terminal and gets to a vertex. So if I'm to connect it with another line, look at what is happening here. Now, what it means is that I have a terminal and I have a vertex and I have another terminal. That is exactly what I have done. So what we call a line angle is because if you look at this, there is a kind of angle. We've drawn a kind of triangle here. That is why we use the word line angle formula. But we're not going to be referring to those angles much in this class. Now, what we're going to be talking about is, like I said, each of these terminal on each of these vertices represent a carbon. However, if we have the line at the terminal, the vertex you have here, we have this as a terminal. Each of the terminal lines represents CH3. Like this CH3, this is CH3. Now, each of the lines at the middle, remember the vertex will always represent, unless there's another molecule there. If it is only the line, this represents CH2. So, as we're going to draw these things, you begin to appreciate these things the more. So this represents CH2. The terminals represent CH3. Now, all the multiple bonds, if you have a structure that has a multiple bond, the multiple bonds must be shown. As even I have a multiple bond in any of this place, the multiple bond must be shown. Now, another thing that will guide you is that in trying to extend or expand the formula, know that carbon will always have 4 bonds. So it cannot go beyond that. Hydrogen will always have 1 bond. Now, see another important thing. If there is another atom that is attached on the chain, on the carbon chain, that atom must be shown with all the hydrogen attached on it. Now, if you have an oxygen like we have here, this oxygen must be shown and the hydrogen attached on it. The only thing we don't have to show is the carbon and the hydrogen. Every other atom must be shown clearly. Let's take this off from there. Now, look at this structure. This one just has a line. This is a line. So we can easily draw this as this point to this point. That is it. This is actually an ethane molecule. That's what we have here. So here it represents CH3, here it represents CH3. You can also draw it this way. This is also correct. You can also make it this way. It doesn't have to be, but it's usually best when you draw it as a vertex, particularly when the chain is longer. But this is okay. We can get away with either this. Okay, let me put all. We can either get away with this or this at this point to represent this one. Now, let's look at this one. If you see this one now, You see, this is a different ball game. Now, another thing you have to do is make sure you maintain the number of carbon chain. Now, let me count this number of carbon chain. This is 1 and this is 1. This is 2. Now, let me count the number of carbons I have. If you look at this, choose any long chain first of all. It doesn't matter at this point. So I'm going to choose 1, 2, 3. And then there is 4 carbon. And there is nitrogen. Remember, every atom must be shown with the hydrogen attached on that atom. So for me to draw this thing now, the first thing I'm going to do, I have a longest chain. So I'm going to try to make a vertex. I'm going to say 1. This is 1 carbon, 2, and 3. So this is 1. Okay, let me use a different color for this. So this is 1, 2, and 3. That's what I have done. Now listen, but there's another carbon attached at this point. So where do I put it? I put it at the middle. So I'll put this here. This is this, and this CH3 at this point. So this will be the carbon number 4. However, we're not done. Now, in this carbon number 2, there is what? Nitrogen attached. So I'm going to now go feed that in. So nitrogen is now attached at this point. And then there is a hydrogen and a hydrogen. Remember, every other atom must have its hydrogen attachment except carbon. So this is how we draw this molecule. Now, let's get to this one. Let's get to the next one really quickly. Now, I'm going to take away this so that I can have some space to draw that. Now, look at this one. This is a ring. This actually has a pentagon ring. Okay, how do we draw that? Look at what we do. First of all, we now draw a pentagon. Remember a pentagon just like you did in your algebra? So this is pentagon. Because this is 1, 2, 3, 4, 5. This is, okay, let's count from anywhere. 1, 2, 3, 4, 5. This is a pentagon. So if you count it now, it's going to give you 1, 2, 3, 4, 5. Now, you're okay with it. Remember, we said every middle carbon is CH2. You see it now playing out here. This is the middle carbon, this is the middle carbon, this is the middle carbon. However, this is different. We have to add this OH. If you add this OH, remember this dry hydrogen, you don't need to show it. You need to put the OH and the hydrogen there. You have to show any other atom and the hydrogen attached on it. We're not done. We said double bond must be shown. Because actually what this is showing us is the type of bonding arrangement. So what do? We must put this double bond. Okay, we now put this and oxygen attached to it. So this is the short form of writing this compound. Okay, let's do the last one. Again, like I told you, try to first of all count the longest chain in doing this. It doesn't have to be like in nomenclature time, we're going to see why this is important, but it's important. So I want to count the longest chain I have here. 1, 2, 3, 4, 5, 6. And I have another one here, 7, as an attachment to carbon number 5. Now, see what is happening here. Two things are playing out now. There is a chain here. There is a double bond here, and there is what? A triple bond. Again, triple bond makes molecule to... Anytime you see a triple bond, every other line after it must be a linear, must be in a straight line because it makes molecule linear. We're going to see this when I refresh your memory once again on the VSEPR model. So what am I going to do? Look at what I'm going to do. I'm going to start with a vertex of double bond. So I'm going to say, I'm going to put this one first. Oh no, I didn't get that. Okay, yeah, that's it. So I'm going to say, I'm going to put this one first. This is a double bond. This is 1, 2. I'm going to take it to 3. Uh-oh, that is not looking good. 3. Oh, it's not looking the way I want it to be. Wait, let me take away everything. So I'm just going to say, I'm going to first of all do this, then I can, okay, this is the double bond. Now remember, this is 1, 2, we're in number 3 now. Now, between this carbon number 3, I'm almost drawing, I'm going to draw a straight line to represent the triple bond. This is how you show the triple bond. So now, after that triple bond, I have another carbon at this point. After this carbon, okay, let me label so far. Let me just try to count the carbon. This is 1, 2, this is 3, and this is 4. So I'm in carbon number 5. After carbon number 5, and I have something different. At carbon number 5, what do I have? And I have this and this. So if I count 1, 2, 3, 4, oh, that's not 5. That doesn't look like 5 to me. Okay, so this is 5 and 6. That's what we have here. And then we have this one as carbon number 7. So this is how we draw it. So what did you observe? Now, the double bond here, we still drew this like a vertex. However, look at what happens here. The triple bond here made this to be linear because triple bond makes molecule to be linear. And in fact, the bond angle usually here is 180 degrees. You remember the VSEPR model. Anytime you have a triple bond, that molecule will likely be a linear molecule. That is why you see this part of it looks linear at this point. So this is how we can draw this. Now, more examples on how to do this. So in this case, what we're going to do now, we're going to be converting these ones into extended or expanded. Those two words will be used interchangeably. So extended again. So we're going to do, remember what I told you? Each of the vertices will represent this. You can even do this, but I just want you to draw it. So let's just draw it. You can make this a straight line. You can make it look slant. It doesn't matter. So I showed you here again. Let me make this a straight line. So I'm going to say this, CH2, and then CH3. You can also open it up completely. You don't have to do this. You can also do this. This is expanded too. Remember, this is the condensed, this is the expanded. But I want you to give me expanded in this case anyways. But it's good I show you that this and this is close to the same. Okay, let's go back to this one. Looks like a pentagon we drew before. Let's do it quickly. So what is it going to give us? Look at what we have here. So I'm going to say, first of all, put the skeleton is pentagon. We're going to try to put it. This is what we have here. And then remember, all these middle carbon are going to have two hydrogens. Remember what I said, that the middle carbon will always have two hydrogens. And then at this point, we have oxygen. So oxygen is attached at this point. You have to show us the hydrogen. Now, if you look at this now, this is not complete. Carbon must satisfy the octet rule by having 4 bonds. Look at this, has 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2. Look at this one, it doesn't have it. So what do you do? This have 1, 2, 3, so you have to complete it with another hydrogen. We go to this one. Now, in this case, again, we have a hexagonal ring. You don't need the names for now, so let's draw them. Just like a hexagon with 6 sides. So, no. So, what do you do first? There's a double bond at this point, we'll put it. And this carbon has 4 bonds, it's satisfied. We don't need to worry about it. And then what next do we do? There's a double bond between these two. And there's a double bond here. Now we have to satisfy, put all the hydrogens to use it to satisfy carbon's octet rule or 4 bond. So here we're going to put 2 hydrogens to make carbon to have 4 bond. Here it has 1, 2, 3, 4 bond. We're going to put 1 here. Here 1, 2, 3, 4 bond. We'll put 1 here. 1, 2, 3, 4 bond. We'll put 1 here. And then 1, 2, 3 bond. We'll put 1, 4. So this is the expanded structure for this. So what about this one? In this one now, look at the way we have. So remember here will be CH3. Here will be CH3. Here, of course, there is 1, 2, 3, 4 bonds. So here will be only 1 hydrogen. And then, of course, here is going to be CH3. So if we open it up, what are we going to have? We're going to have, you can draw it in a straight line. I can do that. So let me make a straight line for it. So I'm going to have C connected to another C carbon here. And this one has this CH attached to it. Of course, this is connected to a nitrogen. Of course, this one has only 1 hydrogen at this point. This nitrogen has a hydrogen connected, and this has a methyl group attached to it. So this is how we expand this thing from the skeletal structure to the expanded structure. In the previous slide, I did the opposite. And it's important we get ourselves familiarized with this because we're going to be doing this a lot in this class. Now, what about the VSEPR model? The VSEPR model simply means the valence shell electron pair repulsion model. Remember what we said, that this comes because we know bonds themselves are electrons, right? We say electrons try to push each other away in such a way that they maintain a maximal distance that determines the overall shape of this molecule. The common bonds we find in organic molecule is common to what we find when we did the VSEPR model. In carbon, carbon can be when carbon is single bonded, it forms 109 bond. And this 109 usually gives you a tetrahedral. Remember, the electron pair geometry will give you tetrahedral bonding, tetrahedral. And the molecular geometry, of course, when there are 4 things attached, will also be tetrahedral. Without lone pair. Remember, when it doesn't have a lone pair. If it does have a lone pair, it changes. If it has lone pair, this changes as well. Here, when carbon has 2 bonds, remember how many? If this carbon, this is carbon. You can use any of them as central atom. If you use the central atom, there are 1. Okay, let me use different color now. Let me use different color and show you, just to remind you. There's 1, 2, and 3 stops attached to this carbon. When there are 3 stops attached to carbon, what do we say? We say the bond angle is 120 degrees. And usually, the electron pair geometry is trigonal planar, and then the molecular geometry, when it has no lone pair, it is also trigonal planar in any case. Now, in this case, when there are 3 bonds attached, just like we saw with this molecule, remember when I showed you this here, I told you this is 180 degrees. That's exactly here. When there is 3 bonds, when there is triple bond, it maintains a 180 degrees. And in this case, the molecule becomes linear. Becomes a linear molecule. If there's no lone pair attached, it becomes, remember, when there's a lone pair attached, the molecular geometry name is different from the electron pair geometry name. And we're going to see that in this. But it's important we remember these few examples as well. All right. So let's see what happens. Let's try to use this problem to digest what I've just said about the VSEPR model. It says, fill in the lone pairs and the bond angles in the following molecules. So what do we do? Now, it is usually best, before you fill in the lone pairs, right? Always draw the complete or extended or expanded structure to show all the atoms so that you don't be confused. So what I'm going to do, I'm going to redraw this molecule to this way. I'm going to redraw it. If I redraw this now, what do I have? You can leave it the way it is bent. You can also make it to be a straight line. So I'm going to leave it, I'm going to make it a straight line to be clearer for you. So I'm going to start with this one. So if I count the number of bonds I have here, I can just say 1, 2, 3. Okay. No, that will be confusing because this is not a carbon. Let me not count it. Let me not do the counting. Again, let me just start from this one. I'm going to draw it the way it looks like. It doesn't matter. So I'm going to start with this one. In this one, I have carbon that is connected to 3 hydrogen, the methyl group. Now, this will now be connected to a nitrogen. This nitrogen now contains another what? Methyl group. Now look at this is now, remember the middle carbon is always CH2. Remember that, we said it. And then this is now connected to another carbon. This carbon is connected to this. And then this one has another CH3. This is expanding this structure. So what do we do? If we want to fill in the lone pairs means we want to make sure that every atom satisfies the octet rule. I always tell you, in organic chemistry, at the level of this structure, at the level of this class, all our carbon will always satisfy the octet rule. It will always have either single bond by 4 or double bond or triple bond. So here it has all the bonds complete. When this carbon now, when there are 4 bonds attached, it satisfies the octet rule. What about this one? What about nitrogen? Nitrogen is 2, 4, 6. Remember what we said in the first part of this class. Nitrogen will always have 3 bonds and what? 1 lone pair. Carbon here has 4 bonds. Okay, here has 4 bonds. Here it has 1, 2, 3, 4. Okay, what about hydrogen? Hydrogen will have 2 bonds and 2 lone pairs. Now it is satisfied. So this is 2, 4, 6, 8. Having done that, we now want to determine the bond angles. Remember the bond angles. Here, what is the bond angle here? There is 4 things attached here. Therefore, the bond angle here is going to give us 109.5 degrees. How many things do we have attached to this nitrogen? There is 1, 2, 3. Remember, the lone pair is an attachment in the VSEPR model. So we're counting this lone pair as an attachment. So this is 1, 2, 3, 4. So there are 4 things attached, and then the bond angle is 109.5 degrees. What about this carbon? 1, 2, 3, 4 things attached, 109.5 degrees too. What about this one? 1, 2, 3, 4, 4 things attached. We also have 109.5 degrees. What about this one? Here, how many things do we have attached here? Remember, in VSEPR model, the number of bonds doesn't matter. If it is a lone pair, we count it as 1 bond, right? We count 2 electrons or a lone pair as 1 bond. We also count the bonds, no matter if it is a triple bond or double bond, it doesn't matter. We count it as 1. So here we have how many things attached to this carbon is 1, 2, and 3. So there are 3 things attached. And when there are 3 things attached, this is going to give us 120 degrees. And this is, we call this tetrahedral, tetrahedral, tetrahedral. This is tetrahedral. This is not going to be trigonal planar. And what about this carbon too? This carbon has 1, 2, 3, 4 things attached to it. And because of that, this is going to give us what? 109.5 degrees. And this is also going to be a tetrahedral electron pair geometry. So it's important we just wrap around our head in some of those things we did in the last class, which builds a foundation for this class. All right, we now go. Okay, sorry, we now have to move forward. We now go to the next one. Now, applying on this knowledge on how to fill up the lone pairs, we're going to move that a little bit further. How to now indicate both the lone pairs. We now say in this problem, it says indicate the bond angles, the lone pairs, and the formal charges of 4 atoms except hydrogen in the molecule. Now, it gave you a hint. It says you must complete the lone pairs before doing it. Yes, that's why they have to do the lone pairs first. For you to be able to calculate the formal charges, the first thing you must do is that you must have to complete the lone pairs. If you don't do that, you're going to miss. Now, the formula for formal charge, you have this in your worksheet, but I'm going to give it to you. Formal charge is equal to the valence electron that the atom has. Remember, valence electron means the number of electrons in the outermost shell of that atom minus the sum of the dots plus the bonds. So this is the formula we're going to use. But before that, let's make sure that every atom satisfies the octet rule. The one that did not satisfy the octet rule, we're going to use our lone pairs. Let's look at this one. Here, nitrogen has 2, 4, 6, 8 satisfied. We don't have problem with this one. Let's look at this one. Hydrogen will always have 1 bond. We are not bothered. What about this bromine? Bromine will have, remember, group 7, 1 bond and 3 lone pairs. Because here it has only 2. So you have to satisfy it with lone pairs. Now I'm going to try to use the red. If I use the red, it's going to be 2, 4, 6 plus 1 bond, 8. What about this hydrogen? Hydrogen has only 1 bond. Therefore, here is abnormal. Usually supposed to have 2, but it doesn't matter for us now. We're going to use the lone pair to complete 8. So this is 2, 4, 6, 8. We go to this one too. Here, nitrogen is 1, 2, 3. Is 2, 4, 6. So we need to use a lone pair to complete it. What about nitrogen? Oxygen. Oxygen here has 2 bonds. So therefore, it has to take 2 lone pairs to make it 8. Here, sulfur is 2 bonds. It has to have this 2, 4. So you need 6, 8 to make it complete. And carbon here is complete. Carbon here is also complete. 2, 4, 6, 8 electrons around it. Now, having done that, we now begin to do what? Let's begin to calculate the formal charge. In all atoms except hydrogen, we're not interested in hydrogen. So in this nitrogen, remember the formula. We say the formal charge will be equal to what? Valence electron minus the dot plus 1. So nitrogen is in group 5. So it has 5 electrons in its valence shell. So what is it going to be? That the 5 is going to be 5 electron minus. Now, the number of how many, the dot here I mean is electrons. How many electron dot? There's no electron dot here, but we have what here? So let me take away this then, since there's no electron dot. But we have how many bonds? 1, 2, 3, 4 minus 4. So this is going to give us plus 1. So what it means, the charge on this nitrogen or the formal charge is, remember, this nitrogen has, this nitrogen has plus 1. And then since it has 4 atoms attached around it, the bond angle is going to give us 109.5 degrees. We now go to this one. Now, let's go to this one. We don't have to deal with nitrogen, right? What about carbon? Let's start from bromine. What about bromine here? Let's start from bromine. So this bromine has, let's see, bromine is in group 7. It's a halogen. So it has 7 minus. How many dots do we have here? 1, 2, 3, 4, 5, 6 dots. How many bonds? 1 bond. Oh, I didn't get that. 7 plus 6 plus 1. 6 plus 1 is 7. 7 minus 7 is 0. It is not charged. It doesn't have any formal charge. So we don't need to worry about it. Now let's look at these 2 carbon. These two carbon will give us the same thing because they are very okay. But let's do it and see. So carbon here, the first carbon here will be this carbon. Carbon is in group 4. Group 4 has 4 electrons in the outermost shell. You should be familiar with this by now. So it's going to be 4 minus. It doesn't have any lone pair, any dot, but it has how many bonds? 1, 2, 3, 4. So 4 minus 4 is 0. So it's not charged. If you look at this, this is the same thing. This is 1, 2, 3, 4. 4 minus 4 will still give you 0. So the carbon in both two will give you 0. So they're not charged. So we're only left with one more thing here, oxygen. So what about this oxygen? Oxygen is in group 6. So it has 6 electrons in the outermost shell. What do? We say 6 electron, which is the valence minus. How many dots does it have? It has 2, 4, 6. It has 6 dots plus 1 bond. So 6 plus 1 is 7. So 6 minus 7 gives us -1. So what that tells us is that the formal charge here is going to be -1. Others are not charged, so they are neutral. You don't have to put them. So what do? But we know that this carbon has 4 attachments. Therefore, the bond angle is going to be 109.5 degrees. This is also going to be 109.5 degrees. And the formal charge here is, so this is 0, this is 0, this is 0. We don't have to show that. When I get to the last one here, then in the last one here, the same thing we're going to do. Let's see this. Now, again, I'm not going to do carbon because here carbon has 1, 2, 3, 4 bond, no lone pair. 1, 2, 3, 4 bond is okay. So I'm only going to go straight to do the nitrogen and the oxygen and the sulfur. So let's start with the nitrogen. This nitrogen has in group 5, so we're going to say 5 minus the dot. It has 2 dots, 1 plus 3 bonds. So which is 5? 5 minus 5 will give us 0. So it's not charged. What about this oxygen? Oxygen here. Oxygen is in group 6. We put 6 minus. It has how many bonds here? 2 bonds. But it has 4 dots. So it's going to be 4 plus 2. 6. 6 minus 6 is 0. It's not charged. What about sulfur? Sulfur is in group 6 like oxygen. So we'll say 6 of it, which is the group, minus. How many dots does it have? 4 dots. How many bonds plus 2? 6. 4 plus 2 is 6 minus 6 is 0. So this molecule, all the atoms here are completely neutral. So we don't need to worry about. The next thing we need to worry about is what? Is the bond angle. Here, nitrogen has how many attachments? 4. 1, 2, 3 plus the lone pair is 4. So the bond angle here will give us 109.5 degrees. What about this one? 1, 2, 3, 4. This is going to give us 109.5 degrees. Now let's look at this one. How many attachments do we have? Anytime you have a double bond, the number of attachments reduces. So we have 1, 2, 3 attachments. This is going to give us 120 degrees. Here, how many attachments do we have? We have this lone pairs are attachment. Remember, this is 1. Okay, let me try to count this one now. This is 1 attachment. This is 2 attachments. This is 3. And this is 4. So there are 4 attachments here. Therefore, the bond angle, let me use a different color there. The bond angle here is going to give us 109.5 degrees. So this is how we deal with this kind of problems. And then you're going to see this in the first exam and quizzes. So you have to be familiarize yourself and practice with most of the things that are provided in the worksheet. And we get to the next one, polarity of molecules. Now, remember what we said, we talked about this in the last part of this class. Polarity of molecule or bond. Now, things that determine the polarity of molecule is number 1, is the change. I'm going to change that color. I don't like it. Is the change in electronegativity, the electronegative bond between the atoms involved. And 2, this is 2, is what? The shape of the molecule. If the shape is symmetrical, it is non-polar. If it's non-symmetrical, it is polar. And the things that can contribute to the symmetry of the bond is what? Is the lone pairs. Lone pairs can contribute to the symmetry. When it has no lone pair at all, it's usually symmetrical. But when it has a lone pair, it changes the dynamics of the symmetry. Remember again, between any 2 types of bond, let's say X to A, when the difference in electronegativity, this is the electronegativity table, remember that. When the difference in electronegativity is less than 0.5, that bond, particular bond is non-polar. And if that bond is not symmetrical because of other bond it has in the molecule, it becomes a non-polar molecule. Now, when the difference is from 0.5 to 1.9, it's polar covalent bond. And then when it is above 1.9, it's ionic. We are not going to be dealing with the ionic part here. Most of the things we're going to be worried about ourselves is between non-polar and polar covalent bond. Let's take that as a problem here. It says in this molecule, what it says, circle the molecules that are polar, draw the delta notation around the polar bond within the molecule that are polar. So the first thing we're going to do, now which of these molecules are symmetrical? Let's see. Carbon here is the central atom. When you look at this, it has 3 things attached. Therefore, it's not even symmetrical at all, which is reasonable. It's not symmetrical. But not just that. This bond is polar. Let's look at the electronegativity. If you look at the electronegativity difference, carbon is 2.5, carbon is 2.5, oxygen is 3.5. If you look at the difference between that, you find out that it falls within this bracket of polar bond. So let's go back. So here, if you look at the electronegativity difference, this is going to give you 3.5 minus 2.5. That gives you 1. So therefore, this is a polar bond because of this bond. So we're going to say the least electronegative is carbon. It's going to assume a partial positive. This is going to assume a partial negative. Therefore, this is a polar bond. So I'm going to circle this as a polar molecule. Remember, what confers the polarity in this molecule is just this bond alone that makes it a polar molecule. Now we go to the next one. What about if you look at this, carbon to, remember, anytime you see carbon to hydrogen bond, it is non-polar. Let me tell you this. Anytime you see a carbon to hydrogen bond is non-polar because carbon is 2.5, hydrogen minus is 2.1. If you do the difference, it gives you 0.4. If you look at this, it falls within this range, is non-polar bond. That's why the first class of organic compound alkanes are non-polar because they contain only carbon and hydrogen. So whenever you see this kind of molecule, take away your attention from the carbon and hydrogen. Go to other atoms it contains. So if you look at this now, these are all non-polar bond. But when you look at this could be a polar bond. If you look at this now, hydrogen is 2.1. Oxygen is 3.5. 3.5 minus 2.1. That gives you a lot. The electronic difference is there about 1.4. This is highly polar. So this is a polar bond. Again, hydrogen is what? Least electronegative. It will be positive. This is more electron. Sorry. Yeah, hydrogen is least electron. It will be positive. Then oxygen will be negative. So what it simply means is that this bond is polar. Because this bond is polar, it makes the whole of this molecule a polar molecule. What a molecule needs to be polar is just one single bond. Now let's look at this. This is a common thing we usually do in Chem 121. Look at this. This carbon to oxygen, like we did here, is a polar bond. This is a polar bond. Look at what happened. This molecule is a linear molecule. In being linear molecule makes it a symmetrical molecule because it contains oxygen on both sides. What it means is that the pool of this oxygen is equal to the pool of this one. So there are two polar bonds, but because it is symmetrical, this bond cancels each other. Therefore, this molecule is non-polar. Because this carbon has the same thing attached on both sides. It is symmetrical. Therefore, it is non-polar. Despite the fact that it contains two polar bonds, but it cancels out. Again, if you go to this one, let's look at this. If you look at this one now, this has only carbon to hydrogen, carbon to hydrogen, carbon. I told you already, carbon to hydrogen bond, non-polar. This is non-polar molecule. Let's look at another one interesting. So this is non-polar, NP. What about this one? This is non-polar bond, non-polar bond, non-polar bond. If you look at this, NH is a strong polar bond because nitrogen, oxygen, and fluorine involves in hydrogen bonding. So but you can also look that up. If you look at nitrogen, nitrogen here is 3.0, hydrogen is 2.1. If you look at the difference, that's about 0.9. 0.9 falls within this bracket. Therefore, this is a strong polar bond. So this bond, hydrogen again is less electronegative. It's going to be positive. This is going to be, so this is going to be what? Negative. So what it means, there are two bonds here. Both of them are, this bond is polar. This, okay, let me use a different color. This bond too is polar. Because of that, this molecule overall is a polar molecule. And then let's get to the last one. Again, if you look at carbon to hydrogen, these are all non-polar bonds. We're not interested. What about carbon to oxygen? Carbon to oxygen is just like, it's something like the one we have carbon to oxygen. It's going to, oxygen is 3.5. This is 1 point. This is 1 point, or again, this is 2.5. If you look at it again, the difference is about 1. So this is a polar bond. What are we going to do? What we're going to do is this. We know that this bond is polar. So carbon here is going to be positive. This is going to be positive. This is going to be negative. So there are two polar bonds on both sides. So this molecule is a polar bond. And we've written out. Remember, the delta notation simply means putting this or this. The more electronegative gets the more electronegative gets the negative, the least electronegative gets the negative. That's usually what we call the delta notation of bonds. Now we now go to two last slides. Now, oxidation and reduction in terms of oxygen. Now, it's important. I'm going to write these ones clearly. Now, oxidation is defined is addition of oxygen or removal of hydrogen. So the opposite, reduction, is going to be the opposite of that definition. Reduction is going to be is the addition of hydrogen or removal of oxygen. So that's what we're going to be seeing in these molecules. We're going to see which side has either more hydrogen or more oxygen, and we're going to decide. Now, listen, oxidation has a shortcut. Oxidation, the shortcut for oxidation is this. You're going to see me do this a lot. And then shortcut for reduction is this. You're going to see me do a lot of this in this class. So what are we talking about? Let's see what happens here. Now, let's count the number. So what it means, what is happening here is oxidation. I've already showed you that. In the next slide, you're going to do it yourself. We're going to try to solve that within that problem and identify. So this is oxidation. If oxidation is taking place, what it means is that we're either losing hydrogen or we're adding oxygen. So let's see what happens. If you look at this place, look at this. In this molecule, in this carbon, there is 1, 2, 3 hydrogen attached to it. Look at 1, 2, 3, 4 hydrogen. Here there's 1, 2. That means it has lost 2 hydrogens here. If it has lost 2 hydrogen, that means this is oxidation. So what that tells you is that this one that has lost 2 hydrogen now, remember, if this has lost the hydrogen, right? Remember what we said here? It has been oxidized. Removal of what? Hydrogen. Therefore, this becomes the oxidized, we say this becomes the oxidized form because it has lost the hydrogen. And the one that has more hydrogen will be the reduced form because it has more hydrogen. Because the more hydrogen it has, the more reduced it is. The more oxygen it has, the more oxidized it is. Or the less hydrogen it has, the more oxidized it is. So both of them go in opposite. Okay, let's look at this one now. If you look at this, now here reduction is taking place. We've been shown that already. In this case, look at what's happening here. If you look at this molecule now, we have hydrogen on this one alone. That's what is changing. This and this is the same. This is the same with this. But look at where it's changing here. This carbon does not have hydrogen. Now it has hydrogen here. This oxygen doesn't have hydrogen. Now it has hydrogen. Therefore, you added hydrogen. This is reduction. What it means is that the one that has more hydrogen will now be the reduced form. And the one that has less hydrogen is going to be the oxidized form. That's exactly what we've done. So in the last of this, look at how you see the question I'm going to pose to you in the first exam. You say, indicate which of these compounds are oxidized or reduced form and show the reaction, where oxidation or reduction, by show whether it is reaction or reduction or oxidation by putting this or this on top of the arrow. So we're going to study both of them first. Let's look at this. This is the same thing with this. This is the same thing with what is changing. Look at what is changing. We have this here, but we added an oxygen. Interesting. Look at that. So there is an addition of oxygen in this reaction. So addition of oxygen, remember, is oxidation. We're going to put it on top of the arrow. So what it means is that this has been oxidized. If this molecule has been oxidized, therefore this is what? The oxidized form. Because it has more oxygen, because this one doesn't have oxygen. And this one that doesn't have that oxygen now is going to be what? Our reduced form. And then we go to the last, but not the least of the problems we have in this lecture. Now, look at this. If you look at this, this and this is the same. The one at this, look at this is the same with this. This is the same with this. What is changing at this point is this. Look at what is changing here. Now, here has one hydrogen, now it has another hydrogen. Here has one hydrogen, here has another. So it has gained technically 2 hydrogens here. So what is happening in this reaction is that reduction is taking place. This is sign for reduction. And that's exactly, this is an alkene, this is an alkane. The difference between an alkene and an alkane is that alkene is the reduced form, is the oxidized form of alkane. That's what it means. So look at what, so it has 2 hydrogen here. So since this has more hydrogen, this will be the reduced form. Since this has less hydrogen, it's going to be the oxidized form. This is how we do these problems. And having said that, we've come to the end of this lecture. Thank you for listening. and have a good day ahead of you. Bye at this point.